Hello, calculus students. This lesson is part 3 of a 3-part series on limits. For this part, we will focus on limits at ends of functions. We begin with a review of 4 classes of functions. Constant functions, y equals k. K can be any real number. This bold capital R stands for all real numbers. That's positive, negative, zero, fractions, pi, irrationals, etc., just not imaginary numbers. For example, y equals 5, climb to height 5, and we have this constant function. Imagine an x-coordinate. As the x-coordinate varies, the outputs of the function remain 5. That's why we call this a constant function. Y equals 0 would be the x-axis. Y equals negative pi. Pi is negative 3.14, placing a horizontal line roughly at this location. Constant functions produce horizontal lines. Now, a couple examples of some limits involving constant functions. The limit as x approaches negative infinity of the constant function 5. As x approaches negative infinity, in other words, as you go left forever on this graph, the outputs are and will forever remain 5. Thus, the limit as x goes to negative infinity of this constant function 5 is simply that 5. Similarly, if you do x approaching positive infinity of a constant function such as 3, you're going to simply get that output 3. Okay, let's look at power functions. These have the form x to the p, where x is the independent variable and p is a constant power. That power can be, again, any real number. In our notes here, let's just assume that we're limiting x to positive values only. Let's use technology to explore different shapes depending on what the power is. Here in Desmos, I typed in y equals x to the p. I created a slider for p that varies from negative 10 to 10. I also plotted the point 1, 1. Let's limit now to x only being positive, so we see only results here in the first quadrant. When p is 1, x to the 1 means just x. We have y equals x. As p goes more than 1, we start to see curves that become increasingly more steep. Notice all these curves are still going through 1, 1, because 1 raised to a power is still 1. As p goes below 1 but stays positive, we get curves that flatten out more and more to the right. When p is 0, we just have a horizontal line segment because a positive number raised to the 0 just becomes 1. And as p goes negative, we get a curve that follows both axes with different curvatures depending on how negative the value p goes. But notice again, they all go through 1, 1. Now, what if I allow for negative inputs? Let me get rid of the restriction. If p is a non-zero integer, such as 1, then negative inputs are allowed. When p is 2, we have our parabola allowing negative inputs. Remember, if you square a negative number goes positive. That's why the range of this function is only non-negative outputs. Here's a complete graph when p is 3, p is 4, p is 5, etc. A complete graph when p is negative 1, negative 2, negative 3, negative 4, negative 5, etc. Pay attention to the different ranges you get, depending on whether the magnitude of p is an odd or even number. But when p is certain fractions, such as 1/2, notice that we have no graph here left of the y-axis, because a power of 1/2 means a square root, and the square root of x cannot allow for negative inputs. However, if p is 1/3, this is a cube root of x. You can odd root a negative number, but you can't even root a negative number. So 1/4 power, which is a 4th root, no negative inputs allowed. But a 1/5 power, which means the 5th root, negative inputs are allowed. Summarizing, when p was 1, we just had a line going through the point 1, 1 and originating at the origin. I put a hollow point at the origin because we're saying x must be strictly positive. When p was more than 1, we had a graph that became more and more steep. When p was between 0 and 1, I'll leave off when p is 0. That just gave us a constant horizontal line. But when p was negative, we had a curve like this orange curve following the axes as asymptotes. Let's do these 6 limits. As x approaches 0 from the right of x squared in its entirety looked like this, and as x approaches 0 from the right, the outputs approach 0. In this case, the limit as x goes to infinity of square root of x. As x increases, although the graph arches to the right, there is no horizontal asymptote. The outputs themselves do go up forever eventually, without bound. So this limit is infinity. X to the negative 1 is just 1 over x. It looks something like this in its entirety. As x approaches 0 from the right, the outputs approach infinity. But as x approaches 0 from the left, in this case, the outputs approach negative infinity. Now, x to the negative 2/3. This means 1 over x to the positive 2/3. The 3 indicates a cube root, and the 2 indicates a power. So this is how you should interpret x to the negative 2/3. The cube root allows for positive and negative inputs, but then the square will guarantee that the output is positive. Looking at technology, and you can see the shape it produces. It allows for negative inputs, but the outputs are always guaranteed to be non-negative. and we have a vertical asymptote because of the division by 0. Now as x goes to positive infinity, you can see the outputs will get closer and closer to 0. That's because this fraction here would approach a 1 over an infinity, which shrinks towards 0. And as x approaches negative infinity, the outputs will also approach 0. Okay, next let's look at exponential functions. Y equals b to the x. Now b is called the base, and for exponential functions, the base must be positive but not be 1. Looking at technology, I have typed in y equals b to the x. Right now the base is at 1, which produces a horizontal line, which is just a constant function, so not interesting. So we don't want the base to be 1. But as soon as the base goes more than 1, such as 2 to the x, 4 to the x, etc., we get increasing or growing exponential functions, including if you let the base be Euler's constant e. Here's a graph of e to the x. E is about 2.718. Now if the base goes less than 1 but stays positive, we get decaying exponential functions. Notice all these functions do pass through 0, 1. So in our notes, you'll get some sort of growing exponential function if the base is more than 1, but some sort of decaying exponential function if the base is between 0 and 1. Let's use these ideas to help with these 4 limits right here. We'll do a limit as x approaches negative infinity of e to the x. Well, e to the x is a growing exponential, but we're letting x go to negative infinity, so we're going left forever. And as we do that, the outputs approach 0. Now let's do a limit as x goes to infinity of 2 to the x. Well, 2 to the x is also a growing exponential, and for growing exponentials, if you go right forever, the outputs increase to positive infinity. Now this next case, we're working with 0.1 to the x. That's going to be a decaying exponential or decreasing. And we're doing a limit as x goes to negative infinity. So if we go left forever, the outputs will increase up to positive infinity. And in this example, 1/2 to the x is also a decaying exponential, but we'll go right forever. And going right forever, the outputs get closer and closer to 0. Okay, and let's look at our last class, logarithmic functions. Y equals log base b of x. This b is still called the base. Keep in mind that this statement suggests that the base b raised to the y would be the same thing as x. And the same restrictions apply, that the base must be positive, but the base can't be 1. Using technology, I typed y equals log base b of x. I let b be 1. Notice there is no graph. If the base goes more than 1, such as 2, notice we get a graph passing through 1, 0. And as we continue to increase, we get a graph that just flattens out a little more quickly, but continues to go through 1, 0. Now it's important to note that for logarithm graphs, even though the graph appears to be flattening out, it does go up forever without bound, as x goes right forever. If the base goes less than 1, we get decreasing logarithmic curves that again go through 1, 0, and even though the graphs flatten out, the outputs go down to negative infinity as x goes to positive infinity. So in our notes, these graphs all go through 1, 0. If the base is more than 1, we have an increasing logarithmic graph. And if the base is between 0 and 1, we have a decreasing logarithmic graph. So we have 4 limits to consider. Log of x is our function. When there is no base written, we always default to a base of 10. 10 is more than 1, so we'll have an increasing logarithmic graph. And as x approaches 0 from the right, the outputs approach negative infinity. Next, we're looking at natural log of x. ln is natural log. And when you see that, you should really interpret this as log base e, where e is Euler's constant. It's about 2.718. It's more than 1, so again we are working with an increasing log function, and this time we're doing as x goes to positive infinity. So as we go right forever, the outputs will go up forever without bound, even though they do so slowly. We'll explore this some more in a moment, but we will get infinite sized outputs as the inputs approach infinity. Now we have log base 0.1 of x. 0.1 is a base that's between 0 and 1. So we have a decreasing logarithmic graph, and we're doing a limit as x goes to 0 from the right, and the outputs will approach positive infinity. And then finally, log base 0.5 of x. Again, this would be a decreasing log graph, and as x goes towards infinity, the outputs will go down towards negative infinity, although very slowly. They decrease without bound. Okay, hopefully you're somewhat familiar already with all 4 of these kinds of functions. Let's go on to the next page. Recall that a polynomial is a combination of terms of the form ax to the n, where a is real and n is a whole number. A rational function is a fraction of 2 polynomials. Find each limit involving a rational function. Confirm some of your answers by graphing with technology. Okay, notice that we're going to let x approach both positive and negative infinity in one step. The degree of a polynomial is the power of the highest powered term, which is a 3 in this case, because that's more than 1. So this is a degree 3 polynomial. 3 is more than 2, so this is also a degree 3 polynomial. As x gets really, really large, it's the leading terms that dominate everything. So this will approach infinite in size, and this will approach infinite in size, although negative, and you'll have some sort of infinity over infinity. This is an indeterminate form. We're not sure what number this is. Don't assume it's 1. The way to determine the limit of this rational function, as x goes to either infinity or negative infinity, is to manipulate it algebraically. Identify the degree of the denominator, degree 3. Then we're going to multiply this rational function, top and bottom, by 1 over x to that degree, so 1 over x cubed, and then distribute. Now 1 over x cubed times 4x cubed will just become 4. 1 over x cubed times 0.2x, some x's will simplify, and we'll get 0.2 over x squared. Now we'll do 1 over x cubed times 6x squared. That will give me 6 over x after simplifying. And then finally 1 over x cubed times negative 8x cubed will give me negative 8. And notice that we just have x's in these subfractions. Now as x goes to infinity, this subfraction will approach a constant 0.2 over an infinite size denominator, which approaches 0. And this would be true whether x is going to positive or negative infinity. Same thing is true for this subfraction. 6 over x will approach 0 as x goes to infinity or negative infinity, which means that we get a limit effectively of 4 plus 0 over 0 minus 8, which simplifies to negative 1/2. And this will be the answer whether x is going to positive or negative infinity. I use technology to graph this function, and now I'm going to graph a horizontal line, y equals negative 1/2, make it orange and dashed. And notice as we go left forever, this graph follows this horizontal line as an asymptote. Same thing is true as you go right forever, the graph will follow this horizontal line as an asymptote. Rational functions, if they have a horizontal asymptote, the graph will follow that horizontal asymptote in both directions. Okay, we have another rational function, polynomial 5x over polynomial x squared plus pi. Identify the degree of the denominator, which is degree 2. So once again, we're going to multiply this fraction by 1 over x to that degree, which is 1 over x squared. Distribute and simplify. The numerator will be 5x over x squared, which becomes 5 over x, and the denominator will become 1 plus pi over x squared. But once again, I see 2 subfractions, so this subfraction will shrink to 0, and so will this subfraction. So in this case, we get a limit of a 0 numerator over a 1 plus 0. 0 over 1 is just 0. Here's a graph of this function with y equals 0 graphed as an asymptote. And sure enough, as x goes to negative infinity, the graph will approach that asymptote. And as x goes to positive infinity, the graph will approach that asymptote. You can compress the x-axis to see that even better. The third and fourth limits here involve the exact same rational function. We'll use the same method. The degree of the denominator is 1, because there's an implied 1 power on that x. So we'll multiply this by 1 over x over 1 over x. Also notice this time we're doing the two limits as separate problems. You'll see why in a moment. Distribute and simplify. We have a limit as x goes to infinity of 5x plus 1 over x over 1 minus 7 over x. Now both of these subfractions will approach 0, but there's also an x here with the 5, and 5 times x as x goes to infinity will approach positive infinity. So this limit will be positive infinity plus 0 over 1 minus 0, which will be a positive infinity limit. Now the same algebraic manipulation will yield this result, but this time we're approaching negative infinity with x. The two subfractions will still approach 0, but this 5 times x will approach negative infinity. So this limit will be negative infinity plus 0 over 1 minus 0, which is negative infinity in size. Here's a graph of our function. Let me change our viewing window. This rational function will have what's called a slant asymptote, a diagonal line guiding the graph, and as the inputs approach negative infinity, the outputs here will approach negative infinity themselves. And as we go right forever with the graph, as the inputs approach positive infinity, the outputs also will approach positive infinity. Now in summary, when you're working with rational functions, you can use some shortcuts. This first rational function was a degree 3 divided by a degree 3. I call this a balanced rational function. The second example was a degree 1 over a degree 2. This is bottom heavy, meaning the degree of the denominator is more than the degree of the numerator. And in this third case, we had a degree 2 divided by a degree 1. I refer to this as top heavy because the degree of the numerator is more than the degree of the denominator. Now it turns out that if you ever have a bottom heavy rational function and you do a limit as x approaches positive or negative infinity, that limit will be 0. If ever you're doing a limit of a rational function that's balanced, equal degree top and bottom, then you're going to get a limit that is the ratio of the leading coefficients. So the lead coefficient of the numerator divided by the lead coefficient of the denominator. So in this first case, that would be this 4 divided by this -8. Hence, we get the -1/2. And when you're working with a top-heavy rational function, the limit as x goes to infinity or negative infinity will also be either positive or negative infinity without any clear way to know whether the answer will be positive or negative infinity in each case. The best way to determine which infinity is correct is to do the analysis like we did above. Okay, let's go to the next page. Consider the 4 classes of non-decreasing functions below, in order of growth potential as x increases toward infinity. So you have constants, logarithms, power functions, and exponentials. Now, constants are horizontal. Notice I'm insisting that the logarithm has a base b more than 1. This will ensure that the logarithm is an increasing logarithm. For the power function, we will restrict the power to be positive numbers. This will ensure that the power function is also increasing. And for the exponential function, we will insist that the base be more than 1 to again ensure that the exponential function is increasing. Now, as x increases towards infinity, the constant function remains constant, so approaches k, but these other kinds of functions will approach infinity. They increase in an unbounded way, but they don't approach infinity in equal ways. Constants don't grow at all. Logarithms grow faster than constants. Powers grow faster than logarithms, and exponentials grow the fastest. So this is a hierarchy of growth potential. Note that any function from a higher class will eventually overtake a function from a lower class. We're going to explore that right now. Consider the constant class versus the logarithmic class. Using technology, I have graphed 2 functions. One's a constant, y equals 10, and another is y equals log base 2 of x, where the base is more than 1. Now, at first glance, it appears that the red function is higher than the blue function. But if we change our scale, we will see that eventually the logarithm will overtake the constant. So in our notes, we have log base 2 of x, and then y equals 10, and there was some point at which the logarithm overtook the constant, and that happened when x was 1024 in this case. This symbol means that the logarithm will be greater or equal to k for some number a if x is more than that value a. So it just means eventually the logarithm will be higher than the constant. Now let's compare logarithmic with power functions. Here I have a logarithmic function in blue and a power function x squared in orange. And it's pretty clear that the power function will always be higher than the logarithmic function. But what if I change the power to 0.3? This is a positive power, so we do have a growing power function. But the claim is that the power function will eventually overtake this logarithm. But let's change our scale to see if that does happen. May need to change the y scale too. And sure enough, in this case, we see that the power function did eventually exceed the logarithmic function and then will forever exceed it. So in our notes, we have log base 2 of x, and our example was x to the 0.3, and we discovered that eventually, when x was around 3,864.7, that the power function did exceed the logarithmic function. And now let's compare power versus exponential functions. I switched my power function back to x squared, a function that grows to infinity rather quickly. And then my exponential function example is 1.1 to the x. As long as the base is more than 1, the exponential function will be growing. And at first, it looks like the power function far exceeds the exponential function. Let's see what happens when I adjust my scale. Eventually, the exponential function overtakes the power function. So in our notes, we had a power function x squared and a growing exponential function 1.1 to the x. And in this case, the point of intersection occurred when x was about 95.7. Now we're going to put into practice is if you have any function from one of these classes, say 2 to the x, a growing exponential, and you divide it by a function from a lower class, say x to the 5th, that both of these functions will approach infinity, but the numerator will approach infinity much faster eventually, forcing this entire fraction to approach infinity. But if you take any function from one of these classes, such as log base 2 of x, and divide it by a function from a higher class, say x to the 5th, that both numerator and denominator will approach infinity, but the denominator will approach infinity much faster in such a way that this expression will be dragged to 0. For now, we'll take this as a given, and later in the course, we will establish tools to prove that these claims are true. Let's go to the next page. Find each limit, confirm some answers by graphing the function using technology. We have 12 limits here. Notice the functions come in pairs. Looking at the first pair, as x goes to infinity, the numerator is 3, and the denominator is a growing power function approaching infinity. Power functions are in a higher class than constants, and these fractions will tend towards 0. Same function, but let x approach 0 from the right. So this fraction will approach 3 over a 0. These outputs are only positive, so this fraction will not have any negative numbers involved as you get closer to 3 over 0. Non-zero over 0 will be infinite in size. For example, imagine 3 being divided by something extremely small, like 1/1000th. After you invert multiply, this is 3,000. If you divide by 1/10,000th, then the result grows to 30,000. So the smaller the denominator gets, the larger the result of this fraction gets. Looking at a graph of 3 over square root of x, we can see that as x approaches infinity, the outputs will decrease to 0. When you zoom out a little bit, you can see that better happening. And as the inputs approach 0 from the right, the outputs of this function approach infinity. Okay, this next case, we have a power function with a positive power, so that's a growing power function divided by a constant. This limit will be an infinite numerator, but divided by a -5 constant. And infinity divided by finite is still infinite, but this will be negative infinity. Same function, but let x approach 0 from above. Well, the numerator will approach 0, but the denominator will stay -5, and 0 divided by a constant is just 0. Here's a graph of this function. You can see that as x approaches 0 from above, that the outputs do approach 0. But as x goes to infinity this way, we have to go far, far out. And as I do this, the y-coordinates decrease without bound. They get lower and lower and eventually fall out of this viewing window. All right, the next functions. Here I have a constant divided by x to the -2. Now, x to the minus power is not a growing power function. It's frankly better to think of this as 7 over 1 over x squared, and then invert and multiply, and we're really trying to analyze 7x squared. So as x goes to infinity, so does x squared, and so does 7 times x squared. So this limit will be infinite. Whereas if we let x now approach 0 from above, this x shrinks to 0, x squared shrinks to 0, and times 7 stays 0. So we get a 0 limit here. Here's a graph of our function. As x increases, then the outputs increase rather quickly to infinity. But as x gets closer to 0, the outputs get closer to 0 as well. Next example is 5 over 1 plus x to the -2. I'm going to think of this as 5 over 1 plus a 1 over x squared, and leave it here, because now I can see that this subfraction, as x goes to infinity, will approach 0, because it's a constant over a growing power function. So this limit, therefore, will be 5 over 1 plus 0, which in the end is just 5. But now, consider what happens when x approaches 0. This subfraction will approach a 1 over 0, which is going to be an infinite size, which means that this overall fraction approaches a 5 over a 1 plus infinity, which is a 5 over infinity, which is effectively 0. So this limit will be 0. Here's a graph of this function. Notice as x increases to infinity, the y-coordinates approach 5, and as x approaches 0 from the right, the y-coordinates approach 0. 4 more examples to look at. As x approaches infinity, the constant -3 stays, but natural log of x is a growing natural log because the base is e, and e is more than 1. Natural log of x approaches infinity, and a finite number divided by infinity will be effectively 0. Next example, we have log without a base, so this is log base 10, which is a growing logarithm, so that will approach infinity while the denominator stays 4, and infinity divided by finite, this will effectively still be infinity. Now we have x approaching 0 from above. The numerator will stay -3, but as x approaches 0 from above, the natural log of x, and here's a graph of it, as x approaches 0, the natural log of x approaches -infinity. So we get a limit of -3 over -infinity, and finite over infinite will be 0. It doesn't matter whether it's positive or -0, 0 is 0. And finally on this page we have, again, x approaching 0 from above. This logarithm is a growing logarithm because the base is 2, and 2 is more than 1. Here's a graph of log base 2 of x. Again, as x approaches 0, the outputs of the function approach -infinity. So this limit will be a -infinity over a constant 7. That will be a -infinity still. Okay, let's go to the next page. Find each limit, confirm some answers by graphing the function using technology. First to consider is there's only one pair of matching functions to consider, otherwise every case is different. In this case, we have e to the -x. Let's address that negative exponent before we consider the limit. I can rewrite this function as 1 over 7 and then e to the positive x. E to the x will approach infinity, and 7 times infinity is still infinity, and finite divided by infinite is effectively 0. Next case, we have a growing exponential divided by a 4. This will be equal to an infinite divided by finite, which in this case will yield positive infinity. Next case, we have a constant divided by a growing exponential, but notice we're now letting x approach negative infinity, so you have to be careful. 2 to the x is a growing exponential, so as we go to negative infinity, 2 to the x will approach 0. And it approaches 0 from above, meaning that 2 to the x has positive outputs. So this limit will be effectively a negative number divided by a number shrinking to 0, which will blow this up to negative infinity. Here's the graph of this function just to confirm. As x goes to negative infinity, as we move left forever, the outputs drop to negative infinity. Next example, we have a constant divided by 5 to the negative x. Let's address that negative power on that base of 5 first, and consider instead a limit as x approaches negative infinity, not infinity, of 4 times 5 to the x. Make sure you don't change that to 20 to the x. The x is a power on the 5 only. But 5 to the x is also a growing exponential, so as we go left to negative infinity, the outputs of this function approach 0, meaning that this limit will be 4 times 0, which is just 0. And here's a graph of this function. As we go left forever, the outputs approach 0. Next example, we have x squared over natural log of x, and x is approaching infinity. Here we can use our hierarchy. This does approach an infinity over infinity. However, power functions will eventually exceed logarithm functions in such a way that the numerator will dominate the denominator and our answer will be infinite in size. Next example, again, x is going to infinity. We have a growing logarithm and a growing exponential. Exponentials dominate logarithms, so the denominator will grow much faster than the numerator in such a way that these fractions will tend to 0. Here's a graph of this function where the outputs do approach 0 as we go to the right. All right, the next two cases, this is where we analyze the same function, but x is going in different directions. I see e to the x is involved. The graph of e to the x is a growing exponential. And in the first case, x is going to infinity. So this e to the x and this e to the x are both approaching infinity in exactly the same way. This is reminiscent of a balanced rational function. You can think of this as the leading dominant term of the denominator, because it dominates the constant. And what I'm going to do is I'm going to multiply by 1 over e to the x over itself, and then distribute and simplify. So x is approaching infinity. We have a 1 over e to the x plus a 3 over a 2 minus 4 over e to the x. And now we have it so that this subfraction and this subfraction, the denominators grow faster than the constant numerators, and they each approach 0 as x goes to infinity, meaning that our limit in the end will be 0 plus 3, or just 3, over 2 minus 0 over 2. Let's now consider the exact same function, but let x go to negative infinity. Well, looking at this graph of e to the x, as x goes to negative infinity, e to the x approaches 0. So this e to the x will just go to 0, and this e to the x will just go to 0. So this limit will be 1 plus 3 times 0, which will just be 1 over negative 4. Now here's a graph of this function. We just made the claim that as x goes to positive infinity, that the graph gets closer to 3 halves. I'll plot y equals 3 halves as a horizontal asymptote. But as x goes to negative infinity, the limit of this function was negative 1/4. Let's make that asymptote. And our technology seems to confirm what we found. We have two different horizontal asymptotes, one for with the function going to the right and one for the function going to the left. Okay, we have x approaching infinity on this next example. Here we have an exponential function over another exponential function. So these are two functions from the same class. What we're going to do here is actually just simplify this. There's a property of exponents that says that a fraction raised to a power, that the power can affect the numerator and denominator individually. We can do this property backwards. In other words, I could write this limit as 0.5 divided by 4, all raised to the x. And 0.5 divided by 4 is 1/2 divided by 4, which is 1/8. 1/8 to the x is a decaying exponential function because the base is less than 1. So graph looks something like this. And as x goes to infinity, this function will decay to 0. Next example, I see a negative power on that x. Also, x is going to infinity again. Let's address the negative power first. This will be a limit as x goes to infinity of e to the x over x to the 5. And the exponential will dominate the power function in such a way that our fractions will blow up to infinity. Next example, it's the exponential that has the negative exponent. Let's rewrite this one. X to the 5 stays in the numerator, but the e to the negative x causes division by just e to the x. And now we have the dominant exponential function in the denominator, so the denominator will grow much faster than the numerator in such a way that these fractions will tend to 0. And then finally, on this page, we have another limit x going to infinity. We have a mixture of classes. We have a power function up above, and then part power function, part exponential down below. Well, the exponential is the dominant term of that denominator. So I'll use this method again of multiplying top and bottom by 1 over e to the x. Distribute and simplify where possible. We can't simplify the numerator much. It's just 5x squared over e to the x. And then all over. We do get a nice 7 to start, and then plus, and then an x over e to the x. These subfractions are not ambiguous. E to the x dominates the power functions in such a way that these fractions will approach 0. So overall, the value of this limit is a 0 over a 7 plus 0, which in the end is just 0. And here's a graph of this function. As we go to the right, the outputs do approach 0. Okay, let's go to the final page. Consider the functions sine of x, cosine of x, and arctangent of x shown below. Then find the limits that follow. If you recall from trigonometry, the solid function is sine of x, and the dashed one is cosine of x. As x approaches infinity, the sine of x just continues to oscillate between -1 and 1 in a periodic way. There is no horizontal asymptote, or there is no single y-coordinate that the graph of sine of x gets closer to. So this limit, as x goes to infinity of sine of x, does not exist. Now as x goes to negative infinity of cosine of x, it's a similar issue. If we go left forever with the cosine graph, it also continues to oscillate between -1 and 1 in a periodic way, and this limit also does not exist. Arctangent, if you recall this function from trigonometry, arctangent is a growing function, but it's bounded. It has a horizontal asymptote to the right of y equals pi halves, and a horizontal asymptote to the left of y equals negative pi halves. So the limit of arctangent as x goes to the right to infinity, that limit is pi halves. Whereas as x goes to negative infinity, the limit of arctangent is negative pi halves. Now all three of these functions are considered to be bounded, meaning that their entire graphs lie within a window of y-coordinates of finite width. So consider this example. We have sine of x divided by x squared. Sine of x itself does not have a limit, but it is bounded, while x squared grows to infinity. So the behavior will be similar to finite divided by infinity, and we'll have a limit of 0 here. Another way to analyze this is to recognize that sine of x, as x varies, has no limit, but it will always be between -1 and 1. So if you divide everything here by x squared, we get that our function of interest is always bounded between these two functions. Let's look at this in technology. Here's a graph of sine of x over x squared. I'm going to reveal a graph of y equals 1 over x squared and another graph of y equals -1 over x squared, and then change my viewing window a little bit. Notice that our graph that's oscillating is always bounded between these dashed curves. But as we go off to the right, the dashed curves themselves approach 0, forcing the red function to get closer to 0. In this case, be careful. We're now going to negative infinity. Be mindful. Cosine of x has no limit, but it is bounded, whereas 2 to the x is a growing exponential, but as we go left forever, 2 to the x approaches 0 from above, meaning it's always positive. And a bounded divided by 0 is an undefined expression. So let's do an analysis similar to what we did before. We know cosine of x is bounded above by 1 and below by -1. So we can say this, which can be then rewritten as -1/2 to the x as a lower bound function and 1/2 to the x as an upper bound function. Well, 1/2 to the x is a decaying exponential, and of course its opposite is a reflection around the x-axis. And so our function always bounces back and forth between these two in some way like this. And as we head this direction with x, we can see that the function that we are analyzing will just bounce back and forth between positive and negative infinity. Here's technology graphing our two functions that are bound our function of interest. You can see that going off to the left, our function will just oscillate back and forth between negative infinity and positive infinity, having no real limit. And so the best we can say here is does not exist. All right, this next example, x is going to infinity again. Arctangent of x will approach pi halves, but natural log of x will approach infinity because it's an unbounded growing function. And a finite divided by an infinite is effectively 0. Here's a graph of our function. As we go to the right, this function will decrease to 0. And our last example, x is going to negative infinity. I just see an arctangent of x right here. This will approach negative pi halves. So the value of this limit will be 2 minus negative pi halves over 3, giving us 2 plus pi halves over 3. You could divide each of these by 3 if you want and say 2/3 plus pi sixth. Here's a graph of our function. We're now looking as we go left. Let's graph our asymptote we just found. And sure enough, as we go left, our blue function does appear to approach this horizontal asymptote. Okay, and this concludes our third part of our 3-part series on limits.